Hey everyone, my name is Phakiso Mtimkulu and I'm from University of Johannesburg, currently doing my BSc Honours in Geography, and today I'm going to be presenting to you the lovely slides on atmospheric circulation. So without any waste of time, let's get into them. So first of all, I'll explain to you the outline of what I'm going to be talking about. And first of all, I'll define what is atmospheric circulation, and I'll also explain the models of atmospheric circulation from simple to more complex model. And I'll also explain the importance of atmospheric circulation in relation to South Africa, why South Africa is special. So in order for me to continue, we need to learn what was the previous talk. So in this case, previous talk, we have learned that light can behave as a wave in particles, and we also learned that air is made up of particles that moves rapidly around. So again, we also learned that when light and air meets, they either can be reflected, absorbed, or scattered. So they results into a blue sky or red sunset. And we also explained that light and air together with Wayne's law are used to explain the greenhouse effect. So what is missing? That is why I'm here. I'm going to explain, and I'm going to fill the gap by explaining the atmospheric circulation. So stay tuned. So first of all, because we want to make this in sort of a story, so we have to understand the hierarchy of models. So it's important to present to you these slides. So first of all, it is explained, a baroque was explained, and a static atmosphere and ocean was also explained. So I am going to present to you the atmospheric circulation, not the ocean. The ocean is going to be presented after this one. So focusing on weather and climate. So without any waste of time, let me take you to the space, because we are going to be talking about atmospheric circulation. So we have to understand that air in the atmosphere moves around in a pattern called atmospheric circulation. So this atmospheric circulation can be defined as the large movement of air by which it is distributed on the Earth's surface. So we have to understand that air can act as a fluid. So when it's heated, it can rise up, and when it's dense, it sinks down. So we have to also understand that atmospheric circulation is influenced by three things, which is Coriolis force, temperature gradient, pressure above the surface, and I'm going to explain that in detail just now. So moving right along. So now here we have to understand that there is differential heating of the Earth's surface from the sun. So there is a shorter distance in terms of heating the Earth's surface at the equator, because the sun is overheating. So now because the Earth is spheroid, at the poles, as you can see here, it's a longer distance. So meaning that the sun heat the Earth's surface in a longer distance at the poles as compared to equator, because the sun it's overhead. So as you can see here at the equator, the distance is shorter, and as you move towards the poles, the distance start to increase. And as you can see, the difference between the poles and the equator here again is coverage. Here the sun rays cover a large area as compared to here at the equator. So this reaches to so now this can be explained as now, because now the sun cover a large area, so now there won't be much heat as compared to the equator. And again, if you have learned from our previous talk, I like to link this because now it makes more sense, as we have learned from light and air. In the light and air, we've explained that here light and air is scattered into a large area, as you can see. That's why in the poles the sun does not shine bright as compared to the equator. It's because of this scattering. So now we are relating this to light and air. And then again, and then as I've explained, here at the equator we are having high amount of heat due to the direct heat of the sun, and then here at the poles we are having less heat. It's colder around here. The air is cold around here as compared to here. So this red represent warm areas actually, and then this blue represents cool areas. So here it's cool around the equator, and around it's cool around the poles, and then it's warm around the equator. So So as we move along, I'd like to explain altitude also plays a role. And as you can see now, the equator is around 0 degrees, which is closer to the sun, and then here the poles are around 60 degrees. This is the latitude as you can see, and then here is the energy, and then the energy here around here there is a heat loss due to the distance and due to the coverage, as I've already explained in the last slides. And here there is a heat gain, so there's a lot of heat around the equator. It keeps on there's a surplus heating, you know, in the tropics, and then cooling in the poles. So this consequent horizontal pressure gradient set the atmosphere into motion, which is what I'm going to explain right now. So we are having this model assumption by George Hartley. So George Hartley assumed that sun is always direct above the equator. So George Hartley proposed in 1735 that the air at the equator is heated and it rises up, and then when this air rises up to a tropopause at a certain level, then it starts to move. It starts moving down. It starts sinking and moving towards the poles, and then when it reaches the poles, it starts to sink, and then when it sinks, it moves back to the equator in a form of surface flow. And then when it reaches the equator, just because it's hot there, just because the temperatures there are warm, it starts to rise again and then move back towards the pole, and then surface flow again, moving back towards the equator. So this process is called convergence. So that's why I'm going to explain more in detail when we go to the next model, you know, convergence cells and whatever. So this one is a gigantic cell, you know, called Hartley cell. It's named after him. And then this whole thing explain a single wind system. So now there is a limitation in this. There is a limitation in this model by George Hartley, and then that limitation is that it does not account Coriolis force rotation. So in reality, we know that F is rotating. So now let's see when we add rotation. So now we have to understand this Coriolis effect or Coriolis force. So Coriolis force is actually the effect that describes how trajectory of an object appears to deviate from the expected path. So now this Coriolis force effect due to the F rotation in the southern hemisphere, the air is deflected on the left, and in the northern hemisphere, and the air is deflected on the right. So this now, in order to explain this in more complex manner, we're gonna have to use this demonstration. So now, as you can see, there are two people. The first one want to throw the ball to another person. So now, because this swing it's rotating, the expected path curls, you know, or it curves. So now this is more acting like a Coriolis force on the F surface. So we can assume that this swing it's an F surface. So now when the ball is thrown, it doesn't go to expected path, which is this second guy. Instead, it curls or it curves. So this is how Coriolis force acts. So now explaining it in more details is when we're gonna explain trace cell circulation model. So moving from a simpler to more complex cell circulation model, which is this one now that explained trace cells, not one genetic cell or one system, which is Hartley cell circulation, moving from equator to the poles. So now this one encountered trace cells, which is ferrous cell, Hartley cell, and a polar cell. So in order to explain that, we have to understand that, as I've already explained, that at the equator it is hot. So since there is a warm temperatures here, so and then the warm air, as I've already explained, that is fluid, it will rise, and then when it rises, it creates what? A low pressure belt. It creates a low pressure towards the F, since it's light, it's on the air. So now it will cause this equatorial low pressure belt. So now, since we have explained in that cell that now when the warm air rises, it moves towards the pole. So when it moves and then reach here, and then when it reach here, it subsides, it subsides, and then when it subsides, it creates what? A subtropical high pressure belt. So because now this air is dense and is subsiding, it will create a high pressure belt, and then this convergence here from the equator, the movement of air from the equator towards the subtropics is called Hadley cell. And then the wind, they are called easterlies, because now the wind are named after their origins. They are called easterlies or trade winds, you know, because now George Hadley, when he explained this movement of air, he explained it in terms of trade winds, because those days they used to sail the ships, you know, sailing from Europe to America. So his model was about explaining how trade winds works, you know. So now in these complex models, as we can see now, they are called easterlies or trade winds. So now moving right along, we are having a subpolar low pressure. This subpolar low pressure belt is created because now the air is converging, it's coming from subtropical high pressure belt, and then there is another air that is coming from a polar regions. So now we know that polar regions, we are having a cool climatic conditions. So now since there is a cool climatic conditions, the air there will be cool, and then it will move towards here, you know, towards here, and then it will converge here. And then when it converges, you can be curious on why now here we're having a low pressure. Why is it a low pressure? Because now here, as I've already explained, that the climatic conditions are cool. So here we are having two land masses. So now, because this one is heavy, the light air will be on top of the dense or cold air. So then it rises up and then creating what? A region of a low pressure. So now the cell here is called a ferrous cell and is in both hemispheres. So this ferrous cell, as I've already explained, is from the warm air coming from subtropics, and then when it gets here, and then there is a warm air from the polar, and then when it gets there, it rises, and when it rises, it creates this low pressure. So the last pressure belt is polar high pressure belt. So this high pressure belt is created, or it is caused, because now we are having a dense air here on the poles. So this dense air, it subsides, as we know that the dense air subsides. So when it subsides, it creates a high pressure here around the poles, creating what? A polar high pressure belt. So now the associated cell here, or associated convergence cell, is called polar cell. So now we are moving to more realistic model. More realistic, it's not real, to more realistic. So now we are having what we call land and water effect. We've already explained the movement of differential heating and all this stuff. So now we have to encounter two things here: the ocean and the land. So land and ocean are not heated equally. So the land is heated faster than the ocean. So as we know that whereby there is much heating, the warm air will the air will force to rise, because now it's warm, and then when it rises, and then it will cool on the ocean. So this explain even more in more realistic manner. And then again, one may ask, like, why is South Africa special? So in order to explain this, we have to look at the change in the seasons. Seasons plays a vital role in explaining this. So you have to understand that when the sun is ahead of tropical of Cancer, it causes to a seasonal shift 5 degrees upwards, you know, along northward, and then when the sun is overhead tropical of Capricorn around somewhere in December, this causes the movement of pressure belts southwards, 5 degrees southwards, you know, causing different seasonalities, different change, you know, in terms of climates due to time. So I'm going to explain this in relation to South Africa. So what's in the news? So as we have heard recently, Cape Town has been suffering from a drought and a water shortage. This is because of seasonal changes. You all remember that there is a seasonal shift. So when seasonal shift is happening, and then around summertime, Cape Town is actually receiving that pressure belt whereby it's sinking. It's actually on Cape Town. So this causes too much sunshine, then no rainfall, end up causing drought and water shortages. So when it comes to Joburg, it's actually opposite. So also during summer season, actually tropical convergence zone moves southwards towards the Johannesburg, move southwards along Gauteng, causing what? Floods, causing high rainfalls that may lead to floods. So this is the difference between seasonal changes. But I was using this as a demonstration for you in order to understand how seasonal changes actually have an effect. But in terms of spatial South Africa, we can see it in terms of different climatic and geographical distribution and different biomes. You know what I mean? So this actually leads because of different climatic conditions, we'll have different biomes. For an example, there are some plant species that adapt to certain climatic conditions. So this actually brings a variety of different biomes in South Africa because of this different climatic conditions. So this is special to us now because now we are having different plants, we are having different plant species in South Africa, we are having different biomes, geographical distribution of biomes all over South Africa because of this climatic conditions. So this is really special to us, And then the importance of circulating atmosphere. It dictates climatic conditions, weather and seasonal traits, just like I've already explained, different seasons, geographical distribution of biomes, just like I've explained on how weather, different seasons leads to different biomes. And it also determines a more comprehensive understanding of functions of the Earth. So now we are able to understand the Earth system in terms of atmospheric circulation, and which is great, and informative. And then in conclusion, summing up, I've talked about unequal heating, which is the main driving mechanism. There is three-cell circulation model, which is more robust. We explained that and its importance to model and characteristics and functions of the atmosphere. We explained that, and then the atmosphere circulation determines the range of climates around the globe and distribution of biomes, just like I've explained that. So in the next exciting talk, as I've already stated, that this is more like a story. Now we are linking everything into every aspect of nature into this. So now in the next exciting talk, we consider the role of fluid in making the planet habitable, which is circulating ocean, and also look the interaction of ocean and atmosphere and how they leads to a process of that makes our planet habitable. And so stay tuned for that. And in terms of references, you'll see references right here. So cheers.